This single line is the foundation of quantum computing. Today I will explain every symbol here in one logical chain. First, forget quantum. Imagine normal 2D space. In normal math, any vector can be written using two directions, x and y. This is just basic linear algebra. Two basic direction. Number tell us how much we move in each direction. Quantum does the exact same thing. These are just two basic direction. We call them ket0, ket1. The word ket simply means column vector. Let me write it here. This is ket. Simply means column vector. And there's another, this is called bra, and this is ket. This is row version of ket, row version of a ket. Okay, this just symbols to represent column vector, and bra represent row vector. Okay, row version of a ket. Now let's rewrite the original equation. This is a qubit. This is a qubit. It is just a two-dimensional vector. Alpha and beta are numbers, usually complex numbers. They tell us how much the state point towards ket0 and ket1. So they tell us how much the state point towards, this is the state, point towards ket0 and ket1. So far nothing new, just vectors. But let me make this more clear. Alpha and beta are just numbers. Just numbers. They can be complex numbers too, okay? They are coordinate of this vector, of this vector. If this were a normal 2D space, we would call them x and y, okay? Alpha is the amount in the ket0 direction. This is the amount in ket0 direction. Beta is the amount in the ket1 direction. Ket1 direction. So this qubit is nothing more than a vector with coordinates alpha and beta. Let's visualize this in 2D space, okay? The horizontal axis, let's label it as ket0 direction, and the vertical, let's label this as ket1 direction. Vertical axis and horizontal axis. So forget quantum for 20 seconds. This is just normal 2D space. Horizontal direction is ket0 and the vertical is ket1. The arrow is our state ket C. Okay, this symbol here is called C. So if I ask how much this arrow lies in the horizontal direction, I drop a perpendicular line here. The length along the horizontal axis is alpha, okay, and that is the coordinate, that is projection, and the vertical part is beta. The vertical part is beta. I hope you can visualize this. And this column vector simply stores those two coordinates, okay, those two coordinates. Alpha is horizontal amount and beta is vertical amount. In normal math, how do we calculate horizontal component? This horizontal component, how do we calculate it? We use dot product. So let me repeat again. Quantum mechanics becomes interesting when we measure, okay? So when we measure in the computational basis, the device can only return 0 or 1. So the real question becomes how much this vector lies in the ket 0 direction. In normal math, how do we measure alignment between two vectors? We use a dot product. This is called bra 0 ket C. This is called bra 0 ket C. Okay, bra is this, 0 ket C, this symbol. Okay, we're gonna be doing dot product here to find the measurement alignment between two vectors. Okay, so we know ket C is alpha and beta vector. Then we know the bra is just the row version of ket, so bra 0 is 1 0. Okay, so we have to multiply these dot product. Okay, so when we do dot product, the only thing that remains is alpha. Okay, the answer is alpha. You can just do dot product. If you don't know, I just multiply alpha with 1, then add that with multiplying beta with 0. Okay, so beta into 0, anything that we multiply with 0 becomes 0. We did it like this: alpha into 1 plus beta into 0. Okay, so alpha remains. This tells us how much the state aligns with ket 0. Okay, it extracts the component in that direction. Okay, let me repeat again. This tells us how much the state, this state aligns with ket 0. It extracts the component in that direction. This inner product is doing exactly what our projection did. This projection. So bracket is not mysterious, it's just projection. Okay, it's just projection. But alpha is not probability yet. Okay, this alpha is not probability. Alpha is amplitude. Amplitude can be negative, amplitude can be complex number, but probability must be real and positive. Okay, so we define probability of 0 is modulus alpha square. We square the magnitude. Okay, we square the magnitude, that gives probability. Let me repeat again. When we measure, the machine can only give 0 or 1. Okay, when we measure, the machine can only give 0 or 1. 0 or 1. That means it only checks, are you horizontal or are you vertical? The more horizontal you are, the more likely you are 0. Okay, you return 0. So here you can visualize it like this. When we measure, the machine only gives 0 or 1. That means it only check, are you horizontal or are you vertical? The more horizontal you are, the more likely you return 0. So probability is just the square of horizontal length. This is why we project. So we square the magnitude, that gives the probability. Okay, this gives the probability. This gives the probability. So let me connect everything, okay, that we have learned so far. A qubit is a vector. Measurement asks how aligned is it with a basic direction. Alignment is found using dot product. Dot product gives amplitude. Square amplitude gives probability. So there is a powerful insight here. In classical probability, you add probabilities directly. In classical probability, you add probability directly. But in quantum mechanics, you add amplitude first and then square it. Add amplitudes first, then square it. Let me explain it with an example. There is 0.5 and there is minus 0.5, and it becomes 0, and when we square it, then it is 0. So the probability is 0. Okay, that means an outcome can completely disappear. This is called interference. That is the core power behind quantum algorithms. Okay, so you might wonder, in classical probability, can't things cancel too? Why cancellation special to quantum? This is a good question. Let's explore it. Why cancellation is special to quantum? In classical probability, all probabilities are real and non-negative. Okay, in classical probability, all probabilities are real and non-negative. Example, event A happens with a probability of 0.4 and event B happens with a probability of 0.3. If there are two ways to get the same outcome, probability would be they always add positively. Okay, they always add positively. You can never have 0.4 plus minus 0.4 because probability cannot be negative. So classical probabilities cannot cancel. You get what I mean, right? Classical probability cannot cancel because probability cannot be negative. So why not? Why not? Because classical probability describes either this happened or that happened. If two paths lead to same result, we just add their chances. There is no phase, there is no sign, there is no direction, just numbers between 0 and 1. Quantum is different. Quantum does not add probability first, it adds amplitudes. Okay, quantum adds amplitude, and amplitude can be positive, negative, and complex. Let me write it here. Quantum is different. Okay, quantum is different. Quantum does not add probabilities first, it adds amplitude. Add amplitudes. And amplitude can be positive, negative, complex. Just like the example I have showed above, like path A, amplitude is 0.5, and path 2, amplitude is minus 0.5, and after we add this, it would be 0, and the square becomes 0, so probability becomes 0. The outcome disappears completely, and that is interference. Okay, that is interference. This interference is the core power behind quantum algorithms. With one qubit, the space has 2 dimensions. With 2 qubits, the space has 4 dimensions. With n qubits, the space has 2 to the power n dimension. All of that exponential growth begins from understanding this vector. Ket C equals alpha ket 0 plus beta ket 1. All of that exponential growth begins from understanding this vector. Quantum mechanics is not mystical, it is linear algebra in complex space. Ket is a vector, this ket is a vector, bra is its conjugate row form, this bra is its conjugate row form, bracket is inner product or dot product, and the square gives probability. Okay, if you understand vector and projection, you understand the foundation of quantum computing. Thanks for watching the video.